Hey everyone, so in this chapter what we're talking about are solids. With our intermolecular forces, we've mainly been talking about gases and liquids. Well, there are some other intermolecular forces out there that explain some of our other solids. So we'll be talking about 4 types of solids today, why they are solids and what forces attracts them together, and some of the characteristics they have to help you identify those solids. So the first solid we're going to be talking about are our metallic solids. Okay, I'm going to be talking about 2 main characteristics with all of these solids, and that's conductivity with electricity and melting points. So be aware of those as I go through these solids. Metallic solids, they are metal atoms surrounded by a sea of electrons. There's no ionic bonding or hydrogen bonding or anything like that to explain why they are solids, so this is one that's in a category all on its own. And the reason that it's a solid is because these electrons are able to corral all those metal ions really close together and form this nice strong bond between those atoms, causing them to be a solid. So you could kind of think of these silver atoms as the cows and the electrons as the cow dogs, corralling them all together. Examples that go under this metallic bonding are any of your metals that you could think of, like gold, silver, cobalt, nickel. Okay, my ring made out of tungsten. Okay, that is a type of metallic bonding. The thing that these guys have characteristic-wise is they conduct electricity in solid or liquid form, right? They have these negative charged electrons and these positive ions for electricity to bounce through. They have high melting points. It takes a lot of heat to melt those guys. Think about things like iron, gold, silver, how much heat it takes to actually melt those down into a liquid form, where they could still conduct electricity. They may be further apart, those atoms, but they could still bounce electricity between those guys. Another thing just to note, some fun characteristics, they're ductile and malleable. Ductile just means they could be drawn into wire like copper wire, and malleable just means they could be flattened into a nice sheet like aluminum. The next thing I'm talking about, we are still in our metals category, but we could have mixtures of metals. And these mixtures of metals are called alloys. Okay, some metals have great properties, but they don't have the greatest properties by themselves, like copper. Copper is a great conductor of electricity. It's malleable, but it's soft. Okay, you try to drive something into copper, it's going to bend or give way. Zinc is a really hard metal, but if you hit it, it will shatter into pieces. But if we mix them together, we could create something like bronze that's really strong and can hold up to strong, forceful blows. Okay, so substitutional alloy is what we're talking about first. It's where we're putting metals of similar size together to give a metal different properties, like I just explained with bronze there. If you look at copper and you look at zinc on the periodic table, they are right next to each other. They have a very similar atomic radius, so we can mix them pretty well without any weird kind of shapes taking form. So what we do is we'll take some copper, we'll throw in some zinc in there, and it creates bronze. Okay, so now it creates this nice stronger metal that could hold up some force from axes or arrows and things like that, and then you can defeat your foes. The next alloy we're talking about are interstitial alloys, and these are alloys that are packed together with smaller atoms so that they can make them stronger. Iron on its own is very brittle. Okay, they used to make tubs out of iron. If you have an old house and somebody wants to take out your old iron tub, all they have to do is hit it with a hammer and it breaks into a bunch of pieces, and it's really easy to carry out. So what they do is they take that iron and they infuse it with smaller atoms and pack those spaces in between those iron atoms in order to make it nice and strong. And that's what steel is. They infuse it with carbon in order to make it strong so that you can't break it or anything like that very easily. They still conduct electricity, both of these alloys. They're just got different properties now. Substitutional, we're substituting in atoms of similar size. Interstitial, we're putting smaller atoms into those metal atoms in order to make it stronger. The next solid we're talking about is one we've already talked about briefly from our intermolecular forces chapter, and that's our ionic solids. These are held together by anions and cations as seen here. This structure here is called a lattice. What you do is you get a sodium chloride molecule or compound. It's got a positive side and negative side, and then it starts to bind with all these other sodium and chlorines and makes this nice lattice structure. if you're able to get a microscope and look at salt, you will see those crystalline structures that these guys form. The properties of these, they have high melting points, okay? That solid is pretty strong, okay? It takes a lot of heat in order to melt those and separate those Na plus and Cl minus ions away from one another. Electricity, this is what makes it different. In a solid form, it will not conduct electricity. Those charges cancel each other out. It doesn't really allow for electricity to flow. But as a liquid, we start heating that solid up and separating those ions. We do start to create a path for electricity to flow through, okay? We separate them a little bit more. Now the electricity is able to bounce in between atoms and create a current. Same as if I took salt and put it in water and allowed it to dissolve, okay? So if I went ahead and I put salt into water, once again, it would separate into those ions, and then I'd be able to conduct some electricity there. So ionic solids, not able to conduct electricity in solid form, but if we melt them or we put them in water, they can conduct electricity. Another great aspect of these is that they are brittle. Okay, this is due to a thing called shear force. If you can imagine me just moving that top row over one, right? If I move that top row over one, we start to get atoms where like charges are right on top of each other. And what happens is those like charges then repel one another. So it doesn't take a whole lot to break these ionic solids. Yes, they have high melting points, but if we hit them with a hammer or just crush them with something, they break apart real easily. They are very, very brittle. Okay, and this is just not salt. This is any ionic compound you have, such as lithium fluoride, iron sulfate, anything that involves an anion and a cation. Our next solid are our molecular solids. Okay, these are solids that contain LDFs, dipole-dipoles, and hydrogen bonding. And you might be saying, didn't we just say that those are gases and liquids at room temperature? Right, but what happens when we increase the pressure or decrease the temperature? Those things will turn into solids. These are things like ice, H2O, when we turn it into a solid, or dry ice, CO2, when we turn it into a solid. So these molecular solids are typically gases and liquids, but we have just made it so cold or increased the pressure so much that they have turned into a solid. And these are known as molecular solids. So nitrogen gas, liquid nitrogen, if we even made it colder, we could turn it into solid nitrogen. So these are things that you typically see as gases, but we just make it super cold to make them solids. Some characteristics of these, they have low melting point, right? Water, dry ice, they turn back into their regular forms at room temperature. They do not conduct electricity, right? H2O and CO2 don't have any free flowing electrons for electricity to bounce through, okay? Pure water on its own does not conduct electricity, right? It's got to have some sort of ions in there like iron or calcium or some fluorine. CO2 won't conduct electricity, right? There's just no electrons there to float around it. And a characteristic of it is that it is soft, okay? They're just softer. It's because they don't like to be a solid. So ice, pretty soft relatively to all other solids. CO2, dry ice, very soft compared to most other solids. And our last solid are those covalent network solids. Okay, covalent network solids are just long chains of covalently bonded atoms. The most common example of this is diamond. Diamond is just this really long chain of carbon. Okay, it's really strong. Okay, graphite is just like that too. It's just not purified as much. Graphite is a very strong solid with a very high melting point that does not conduct electricity. It's just a long chain of carbons. You see this in silicon carbide as well, which is a type of computer chip or formula they use for computer chips. For your solar panels, they use like a silicon manganese combination. That's a covalent network solid. So these long chains of covalent bonds are just really strong. They have very high melting points. Think if you tried to melt a diamond, how hot you would have to get it to be. And they don't have any conductivity. There's no electrical conductivity whatsoever, no free flowing electrons for electricity to transfer between atoms. So those are our 4 solids. You got metallic solids that conduct electricity in solid or liquid form and have a high melting point. You have our ionic solids, which are very brittle, high melting points, but don't conduct electricity in the solid form, but do if you melt it or put it in water. You have your molecular solids that have very, very low melting points, things like water, CO2 when we make them into solids, and they don't conduct electricity whatsoever. And then finally, you have our covalent network solids that have a very, very high melting point and don't conduct electricity whatsoever, that are just those long chains of covalent bonds. So that is our solids lesson. Know those 4, have them down, and make sure you're able to identify them based on those characteristics of melting point and conductivity.